up. Did it pop up yet? There we go. Perfect. Have a great session.
Okay, so you're seeing my slide over there. I take it. My name is Kevin Farley. I'm a Senior Program Manager at Microsoft in the SQL Server group. Specifically, I work in the SQL storage engine, which is that layer of SQL Server where SQL meets the physical storage. So I spend a lot of time dealing with how SQL Server interacts with I/O systems, how to make it go fast, and optimizing it, keeping on top of new developments and the like. My history is that I've gone back and forth between the storage world and the database world in my career, and this is a really nice slot in that I'm joining both together. We're going to start by giving a little bit of background on what I/O is about, a common terminology. One of the problems that I find dealing with I/O problems at customers is you're typically dealing with at least two people, the database administrator and the storage administrator. And that seems like not a big problem. But the issue tends to be that the DBA and the storage admin rarely speak to each other. And if they do, they don't have a common vocabulary. So it makes it really hard to get things accomplished, because the DBA is thinking in terms of transactions per second, and the storage just isn't letting me go fast enough, and the storage admin is thinking in terms of capacity. I've got enough bytes. What's your problem? So we'll start out by setting a level for what our terminology is and how we think about it, and then we'll go from there. So start by what's an I/O. We're dealing with I/O performance. We need to understand how we think about an I/O and what metrics we use to measure how we're doing. So there's three dimensions we look at I/O performance for a database. There's throughput, latency, and capacity. Drilling in a little bit deeper, throughput is how fast can you get bytes from the storage media to the processor. And that's measured in either megabytes per second or in IOs per second. So what's the distinction? Megabytes per second is just raw throughput. How fast can you transfer bytes from here to there? Big fire hose. IOs per second is how fast can you do transactions, or how many transactions can you do in a unit of time. And we measure those using perfmon. Typical counters would be disk read bytes per second, write bytes per second for the throughput in megabytes per second, and disk reads per second and writes per second for IOPS. So that's how quickly can you do IOs individually, or how many of them can you get done in a unit time. The second matrix would be latency, and that's measured in milliseconds typically, sometimes microseconds. And that's how long does an individual I/O transaction take. So transaction in terms of the interaction with the I/O subsystem. And that's measured, again, using perfmon in terms of seconds per read and seconds per write. And later on, I'll get into what are healthy latency values. But there's a lot of confusion between latency and throughput. People get them confused or think they're the same thing because they're both facets of performance of the I/O system. I like to use the analogy of a cocktail straw. So little straw used to put in the cocktail. It's pretty thin, pretty short. You blow through it. It doesn't take very long for the air to get from end to end. That's latency. How long does it take to get from here to there? Throughput, think in terms of running a foot race and breathing through that straw. You can't get very much through it. Even though it goes from end to end very fast, you're not getting much through. That's throughput. So that's kind of the distinction that I draw between those two. The third dimension is in capacity. That's the easy one. It's how many gigabytes or terabytes do you have in your subsystem. And again, the rub here is most storage admins are measured on their utilization of capacity. And that's typically how they think in terms of laying out I/O for any of their consumers, is do they have enough storage to meet their needs? Storage defined as capacity. That may or may not give them the throughput and the latency specifications that they need. So let's talk about the connections between the processor and the actual storage media. Three basic scenarios are direct attached storage. It's the simplest data path, less to go wrong, less potential bottlenecks between processor and storage. It's the fastest, lowest latency, lowest functionality. I find two classes of customers typically use direct attached storage. Customers on the very low end of the spectrum in terms of functionality and budget, and customers on the very high end that have very stringent performance requirements, can't tolerate the extra latency and potential bottlenecks in the path introduced by all the components between the disk and the processor. Again, it's the lowest level of functionality, which means that a lot of things that the SAN environment would do for you, you have to do by hand. All the layout is done by hand. You're physically configuring each individual disk spindle and configuring it to a volume. And so if you don't get things laid out optimally, going back and changing it later is a real problem. There's no level of virtualization, so it's typically shuffling all your data back and forth. It's going to involve a lot of downtime. You really want to plan things carefully and get it right the first time. Probably 99% of the databases I deal with are on SANs of one flavor or another. There's fiber attached is by far the most common. iSCSI, you can sort of throw NAS devices into that now because some of the file share protocols, the SMB3 especially, are getting to be very performance competitive with fiber channel. I can go into that towards the end if I get enough time. SANs give you a lot more management options. Essentially, SAN is a special purpose computer wrapped around a lot of storage. So they have a lot of virtualization. They will take a collection of individual disks and logically group them all into a big pool of storage. So you can think of all that capacity of all those different disks as one pool, and then you just carve out units of capacity and or performance as you need it and expose that as volumes to your servers. And the other thing is that SANs can be shared among a lot of servers. So that means that you have better utilization as opposed to each server having to maintain enough spare capacity for whatever growth might happen. You can now amortize that extra capacity over a lot of servers and get by with less total storage. So you get better utilization of the storage that you have. Management is easier in a SAN because you're managing one array for a number of servers rather than managing that server on each individual server. It can be cumbersome to set up. A lot of the reason for that is that each vendor has their own set of utilities and tools for managing the storage, and different vendors think about storage differently. So you'll have different abstractions that you have to understand in order to lay out the relationships between the physical media and in the end, the logical objects that you're putting on them. But again, once you understand that, once you set that up, you have a lot more flexibility in terms of tuning things and changing them after the fact. Auto-tiering is just a flavor of SAN, which is becoming more and more common these days, and that's where the array may contain multiple classes of storage. So you may have 15K RPM drives, 10K drives, SSDs, and maybe even some slow SATA drives for bulk storage. And the array automatically migrates data between these tiers based on usage patterns. So let's take a look at just visually what's the path between the drives and the processor. For direct attached, again, it's a very simple path. You've got your CPU, your processor, and memory attached to one or more PCI buses. In a good-sized server, that's typically going to be many PCI buses. And then you have a number of disk controllers. Most database systems would be a SAS controller, serial attached SCSI. And each SAS controller is connected by a cable or multiple cables to disk shelves containing multiple independent disks. The disk shelves may or may not have a RAID controller that is capable of pairing the drives in RAID sets. But you can see it's a fairly simple topology there. And one of the keys to that is when you're thinking about storage from a performance standpoint, every component between the processor and the disk spindle, including both ends, can be potentially a bottleneck. So I've seen systems choke on CPU capacity, limiting the ability to move data, just straight movement of data. PCI buses can saturate. Disk controllers obviously have capacity limits. The protocol over the wire, so effectively the cable, and then the disk shelves and disks themselves all have limitations for how much performance they can deliver and or transmit. Comparing that to a SAN configuration, the left side is the same. You've got the same processor, the same set of PCIe buses, and then in place of the disk controllers you have host bus adapters, which are simply an adapter between the PCI bus and fiber channel, which is the typical fabric that is used to communicate with storage arrays. Typically you'll have redundant paths between each server and the array going through multiple switches to an array of ports on the array, fiber channel ports on the array side. And this gives you a topology where there's no single point of failure between the system and the storage. The disks themselves will be paired up in some RAID configuration, so you have multiple disks serving an individual piece of data so you can survive the failure of any disk. There will be multiple storage controllers. Again, that array is itself a special purpose computer. The array will have some volume of fast cache, and that's used to serve data out of it. So if a piece of data has been fetched from the physical storage and delivered to a server, it'll be stored in that cache. In case someone wants that same piece of data again, we can just retrieve it from the cache without going to the physical storage. Likewise, on the write path, if a system needs to write data, it'll go into that fast memory, and then the array can destage it into the physical storage as it has time. And as long as that array is backed by batteries, which most enterprise class arrays would be, then we don't worry about the fact that the data isn't hardened to spinning media right away, because if there's a power failure, the batteries will provide the array with enough time to drain that storage away, drain that data away to the physical storage. So you can be assured of that. Again, any of those components can potentially be a bottleneck in performance. So you need to be able to monitor all of those components to understand where you might be having a performance issue, where you're running out of capacity.
Kevin,
yes.
Sorry to interrupt. Can I get you to put your slide up full screen? Is that possible?
Okay. What are you seeing? Because I've got a full screen here.
I'm only seeing it with your slides at the bottom, where you're spanning through, and just the actual slide to the left.
Ah, okay. Let me see if I can change that. Is that better?
That is better. Yep, thank you.
Certainly. My idea of monitor 1 was different than their idea of monitor 1. Sorry about that. Okay, so getting back to the physical layout here, this is just illustrating the idea of a tiered storage where the array has multiple classes of storage. So the red disks might represent solid-state drives that are extremely fast, but somewhat expensive, so you're not going to fill your whole array with them typically. The green would be a mid-range drive, which might be 15K RPM drives, possibly 10K, and the blue drives would be large capacity spindles for cold storage, so storing data that needs to be kept online but isn't necessarily accessed that frequently or with such stringent performance requirements. So possibly even SATA drives, something that is economical to store large volumes of data. Tiered storage solutions, again, in comparison with standard SAN, you can accomplish the same tiering of storage with a regular SAN without any of the fancy tiering features, but that means that the storage admin and the DBA cooperatively are responsible for all that intelligence of what data gets placed where. And it really makes a lot of sense to think about placing data objects on the most appropriate class of storage, because you don't want to have to populate an entire $1-million array with the most expensive class of storage to meet any of the requirements and then end up spending that expensive storage storing Word documents or some class of storage of data that just isn't that critical performance-wise. So that means making the association between data objects and physical storage is up to, again, the DBA and the storage admin cooperatively. And the granularity is up to whatever the admin decides to move. As data changes, so for example, you may have hot data that's this week's orders and cold data which is last year's orders, historical information. At some point this week's orders become historical information. You have to move the data from here to there, and that's an explicit operation that has to be done to migrate the data from place to place. With tiered SAN, all of that is done for you. So the SAN has the intelligence to observe access patterns, what data is accessed most frequently, etc., and migrate data in the background in an online fashion between slow storage and fast storage or vice versa as access patterns change. And there's a fair amount of very sophisticated IP that goes into determining when to make those moves to optimize performance overall. You don't want to, for example, do a one-off report that scans a huge volume of data and have that cause all that data move into the fast storage, because you may not access that data again for a year. So again, the success of the tiered storage is dependent on the array being able to guess correctly what data is going to have the highest performance requirements without the array being aware of what that data represents. It's just blocks as far as the array is concerned. It has no intelligence as to what that storage represents. So that's tiered storage. One comment from a database perspective in terms of the idea of SAN as a pooled storage resource. It's a very attractive concept in that you get to share the capacity, and even from a performance standpoint, by sharing a large pool of storage, you can typically spread access to data over a large number of disk spindles, which tends to increase your performance over time. There is a possible hitch with that, however, as this graph demonstrates. This is a perfmon chart. The green line is checkpoint, which is an operation SQL does occasionally to flush dirty pages out to physical disk storage, to the data files. The black line represents the latency, the time for each write to take, and the red is your transactions per second, so how fast are we doing database operations. And you can see as we have a checkpoint operation that spikes write activity, so it takes the write activity way higher than it has been steady state, the latency, because we're doing all that writing to the data drives, goes way up, and your performance, which is what the end user actually sees, goes way down. So this is just a caution to say that it's not enough to measure steady state and know that you're okay at steady state. You have to measure your most stringent spikes in I/O requirements to make sure that you're going to have enough capacity to meet those. So now I'm going to walk you through an example of going from requirements for a system all the way through choosing the hardware to meet those requirements, and then validating once the hardware is in place that we actually are getting the results that we calculated on paper that we would get. So the project at hand, this is an actual customer example. It's a 10 terabyte data warehouse, not exotic by today's standards by any means. The customer had requirements that he had a very definite price ceiling. So it had to be fairly inexpensive hardware. Had no need for HA because this was data that could be reconstructed. Obviously there's a time cost to that, but it wasn't critical that it always be online. It's for reporting. It's white box, so build your own server. SQL has what we call fast tracks, which are defined configurations that we've worked with various server vendors to come with off-the-shelf configurations for various purposes. And we have one for data warehouses. However, it uses MSA 2000 fiber-attached shelves, which were a bit too expensive for this customer's particular budget. Looking at that third metric, capacity, so how much data do we need? The total storage need is 10 terabytes. That's how much data, end data the user needed to keep up. We're using 450 gigabyte spindles. That's the disks that had been chosen for this configuration. So that's 25 spindles. Using RAID 1 for redundancy and also for performance. We'll get into that in a second. We're doubling up those spindles, so it's 50 spindles. May need a few hot spares just in case a disk goes bad. So the estimate for that particular class of disks is 120 to 125 megabytes per second per spindle. And again, this for data warehouses, we're concerned mostly with the megabyte per second metric rather than IOs per second. We'll get into that in a bit. The building block is RAID 1 pairs, so 2 disks in a redundant RAID 1. For read performance, a RAID 1 pair can deliver double the performance because you can read from both disks concurrently. So that gives you 240 to 250 megabytes per second for each pair. Write performance is half that. That's about 120 megabytes per second because you have to write to both disks. So that's how much the disks themselves can deliver. But we've got that whole path to consider. So you have to make sure that we can actually consume that much performance. So look at the interconnect. Each shelf, between the shelf and the server, given the SAS protocols, each shelf can deliver 1.2 gigabytes per second. The array controllers that we're using on the server side can deliver 2 gigabytes per second. So that will work well. It means that the controller won't limit the bandwidth. The shelf will deliver enough performance to consume all the performance of the drives within them. So we have 1.2 gigabytes per second, 1 controller per shelf. 5 controllers and shelves gives us about 6 gigabytes per second. Each shelf will hold, we've got a total of 50 drives divided by 5 shelves, or 10 drives. So we pack 10 active drives into each shelf. MSA 60 is a shelf that happens to be a good match. It holds 12 bays. It has the right characteristics for what we're trying to accomplish there. We only need 10 of those, so we'll put 1 hot spare in each shelf, giving us ability to repair for any drive that may go bad. And we'll just leave 1 bay empty because we don't really need 2 hot spares. So total rack space 2U times 5 is 10 U's for the storage. Choosing CPU and memory, for 25 RAID 1 pairs, we chose to build a box with 24 cores. For this generation of processors, the calculation average is that these cores can consume 200 megabytes per second per core. It's not quite a match, but we think it's close enough. Memory, we want the memory to be big enough to hold the largest partition. What that does is it allows you to rebuild indexes and do sorts without spilling the sort to disk storage, which slows things way down. Customer went with a 256 gigabyte storage or memory configuration. So now we've got the end-to-end system here, and that's physically what it looked like. The server's in the bottom. We've got 5 shelves of storage, which we just saw. You can notice that one of these bays is empty in each shelf, just like we discussed. The log drives are in the internal drives within the server itself. The top shelf is for another purpose, for analysis services. So on paper, we've got a system that will do exactly what the customer needed it to do. Let's see if we actually achieved that. So the first step is we test one RAID pair. So we configure one pair of disks on a shelf as a pair and see if we can read 240 to 250 megabytes per second. SQL.io is a free tool that SQL you can download from Microsoft, and it emulates various patterns that are common within SQL Server for I/O. So this is doing 8 outstanding, queue depth of 8, 1 thread, read workload, 512 byte I/Os, and the results from that are 240 megabytes per second. So that's exactly what we calculated it should be. Nice. Okay. So let's scale it up. Go to the next layer. Test a shelf. So build 5 RAID 1 pairs, which is how we had decided to configure the storage on a shelf. Run SQL.io on all 5 at the same time using 5 data files, 1 for each RAID 1 pair. We expect to get 1.2 gigabytes per second, which is the limit of the cable, and we in fact get that. So things are looking good at this point. We're able to get in physical reality what we calculated we would get on paper. An optimization you may want to do is disable read caches on the devices, since the array is handling that for, or the controllers are handling that for you. So let's test it all out. Add up all 5 shelves, run SQL.io across them all. First problem we run into is that SQL.io runs out of thread. Okay, not a big problem in that you can run multiple iterations of SQL.io, and rather than getting the nice report directly out of SQL.io, you can get the performance out of perfmon to find out what your performance is. And the aggregate performance from all 5 shelves ends up being 4.5 gigabytes per second. Not what we anticipated from scaling just the storage. And that gets back to what I said earlier, that any component along the line can be your bottleneck. If you remember back to the discussion about choosing CPUs, we said that each CPU could do somewhere on the order of 200 megabytes per second per core, and we had 24 cores. Doing that math, that comes out to right around 4.8 gigabytes per second, so that explains why we're not getting the full 6 gigabytes per second. Going to a beefier system would have given us the full 6 gigabytes a second. However, that would have also cranked up the cost of the system significantly, and for this customer, this was the right trade-off. So a nice illustration that you can have bottlenecks at any point along the way. Another way to look at that is to look at this shape. So what are we looking at? Interesting looking graph. Okay, so the black line is in disk read bytes per second. So this is again bulk throughput performance, and obviously things are happening to the system in those intervals. This is a significant span of time, so you're going over about a 10-minute interval here. So each of the small steps is adding a disk pair. So again, we have multiple disk pairs within an array. This isn't the same system as I just described, but it's a very similar configuration. So the small steps are adding disk pairs, but then you hit a plateau where adding another disk pair isn't going to help you any. So what do you do about that? Okay, that's when you have run out of capacity on an individual shelf or controller. So we add another controller. Again, we go back to adding RAID disk pairs. But we notice that those plateaus are getting closer together and longer. So we're running in, and eventually things tail off and don't follow the same pattern. So something else is going on. And in fact, what we hit on this system is the backplane limit, the aggregate of the Northbridge, Southbridge chips, as well as the PCI buses. So that's the capacity of the system as a whole to consume data was greater than the storage itself. And again, you see we're getting 140 per shelf, and then it starts getting smaller, and then you run out of capacity. So it's just an illustration that there's a lot of different ways that you can find potential bottlenecks in a system. And shift gears a little bit and talk about workload-specific I/O best practices. So different I/O workloads you'll see in the SQL Server ecosystem: online transaction processing, OLTP, order systems, inventory, fast data churn. They're going to typically see heavy on 8K random reads and writes to the data drives, some amount of Readahead. The size of the Readahead is going to vary. It's always in multiples of 8K because that's the internal page size within SQL Server. A lot of times you'll see mixed workloads with some reporting happening on an OLTP system. The other definite I/O pattern for any SQL Server is the transaction log, which is always sequential writes. So if at all possible, you want to isolate the transaction log to separate physical storage so those disks can do nice sequential storage, which is much faster than random I/O. Relational data warehousing. So a data warehouse hosted on a relational database is going to have typically 64 to 512K reads. So you're doing scans of large volumes of data. 128 to 256K writes for bulk loads. You typically bulk load the data warehouse and then do reporting out of it. So the rule of thumb is that you want to optimize for high aggregate and throughput I/O, which is what we just went through in that example that I walked us through, as opposed to online transaction processing where you're optimizing for random I/O and for I/Os per second. So you're optimizing in the OLTP case for how many individual storage operations can you do per second versus how many bytes can you flush through the system end to end. Analysis services is a separate storage engine on the SQL Server end. It tends to use 64K random reads, often very fragmented data. So you're going to optimize for random 32K blocks in your I/O patterns. Diving a bit deeply into the OLTP workload specifics, I/O patterns are generally random in nature. So OLTP, you're doing point fetches of specific data. So you're going to look up a specific customer. You're going to go look up an inventory for a specific part to find out how many you have in stock to see if you can fill an order. Those sorts of operations. Decrement the order, the inventory cost while you create an order for that number of the parts. So you can have very randomized I/O in various areas of your storage. You can have heavy bursts of writes. So again, that checkpoint that I mentioned, when you've updated a number of pages within the SQL Server's cache, eventually we need to make room for more data, so we're going to flush data out to the physical storage, and you'll see a flood of write I/O to various random places. We'll consolidate as much as we can, but there's a limit. And you're going to see a steady stream of writes to the transaction log. And transaction log is the most performance critical component in the system for OLTP workloads, because writing to the transaction log is in line with each individual transaction. So as we commit, before we can return the commit to the application, we have to be ensured that that write has made it to durable storage. In the case of the SAN, that may be the battery-backed cache, but still we have to make it that far before we can declare that the transaction is complete. Many OLTP deployments consist of mixed workloads with some amount of online reporting, so you'll have some scan behavior, so you do need to pay some attention to the aggregate throughput. But again, the overall dominant characteristic is the random I/O. Some do's and don'ts for OLTP system: size based on spindle count. So an individual spindle or disk will be able to deliver some number of IOs per second. And it can vary widely depending on the class of storage, whether it's a SATA drive or an SSD, hugely different numbers. But still, for whatever class of storage you're using, each unit will deliver some number of IOs per second. If you understand either through observation of your current server or calculation based on your proposed workload how many IOs per second your database is going to require, you're going to calculate how many units you're going to need to deliver that number of IOs per second. It's highly likely that that won't be a complete match with the volume of data stored on those pieces of media. So that means you don't store size based on capacity. You may need 10 physical drives to store the volume of bytes that you need to store all of your data, but in order to deliver that number of IOPS, you may need 10 times that number of drives. So that means that each drive is going to only use a small percentage of its byte capacity in order to fully utilize its IOPS capacity. Again, another metric you want to pay attention to when sizing for OLTP is the write IO latency on the transaction log. And that, again, can be improved by using RAID 1 to spread that I/O over a large number of physical spindles. As we saw, checkpoint operations can be challenging to the I/O system, so you want to make sure that you test the effects of checkpoint, in other words, a large flood of write operations on an ongoing workload to make sure that you have enough capacity to absorb that much behavior. A little bit about the transaction log, because that is a very performance critical part of the SQL Server. Internally, the transaction log is made of virtual log files, or VLFs. It's just a way to logically subdivide the physical transaction log file, and VLFs are the units at which we reclaim file space. Within SQL Server, the transaction log is treated as a circular buffer, so we'll fill VLFs from end to end, and as the VLFs are not needed anymore, they can be recycled and overwritten. So we'll just start again at the beginning and go back to the end at the granularity of VLFs. When you're switching to a new VLF, we have to format the 8K header for each virtual log file, and that's a synchronous write, so that's going to cause pause. So for that reason, and for a number of other reasons, you really don't want to have more VLFs than you have to. There's processing that happens at database startup time, which has to scan all the VLFs in the log file. So the more VLFs you have, the longer it's going to take to bring your database online at the beginning. We have to look through the log to make sure that there are no incomplete transactions that need to be rolled back before we let you see the data to make sure that it's in a consistent state. A trap that some customers find themselves in is that they size their log file based on what they think is going to be required, and they may leave the growth increment of the log file either at the default or explicitly set it to a very small increment. If some unusual operation happens that causes that log file to have to grow significantly, if you're growing, each growth increment adds 4 VLFs, so we'll subdivide each growth into 4 VLFs. If you're growing 1,000 times, that quickly adds up lots and lots of VLFs, which makes things rather less than optimal in terms of efficiency. Depending on the size of your log file will have different numbers of VLFs that will be in the original log file, somewhere in the range of 16 to 32 VLFs, I believe. We had one customer that got themselves into a world of hurt by having their log growth increment set to 1 megabyte, and sometime over a weekend when nobody was watching the system very closely, a transaction hung which kept any VLFs from being reused because there was data in that original VLF that was still of interest, might have had to be used to roll back that transaction. Because of that, we couldn't recycle log space, and that meant we had to grow the log to keep the system online. By the time the system came to a screeching halt because they ran out of disk space for the log, they had 400,000 VLFs within that log file. You can imagine that that's not a very optimal situation. Starting off every one of those transactions at 1/4 of a megabyte of log space caused a pause as we reinitialized that VLF header. What happened at that point, though, was someone took the system offline to add more capacity to the log file, brought it back online, and we started scanning 400,000 VLFs for any transaction data that might be needed to bring the database back into consistency. At the time, we had a less optimal algorithm for doing that than we do today, and we ended up scanning the whole log file repeatedly. The estimate for bringing the database online was 18 days. Now that's a huge problem for any business. This happened to be the system for a hospital, which caused major consternation. So we had people working 24 hours a day back here in the product group to fix that problem. And we have made it more optimal. But the major point is you don't want to be in that situation. So you need to monitor the number of VLFs in your log. There's a command dbcc log info which will tell you how many virtual log files you have within your log, and you can rebuild the log to consolidate. And the other takeaway from this is when you have to grow your log, make it a planned event, grow at a significant increment rather than let it grow in small increments. A little bit about SSDs, just a quick comparison of SQL Server running on SSDs versus spinning media. This is a set of metrics that were done using an EMC DMX4 array. RAID 5, 3+1. This is looking at SSDs. Only 4 physical devices to deliver this much I/O performance. 300 gigabyte database, random read and writes for checkpoints and sequential log writes, all sharing the same physical devices because seek time doesn't matter on solid state media. Had a 16-core server, completely CPU bound. That means that we weren't bottlenecked in any way by the I/O system. We were using every bit of I/O that the system as a whole could consume. The counters we look at, seconds per read latency is 4 milliseconds. Reads per second is 10,000. Seconds per write is 1 millisecond. Writes per second, 1900, almost 2000. 97% processor, and 5100 SQL transactions per second. Comparing that with spinning media, so we achieved about the same rate of disk reads per second and disk writes per second. However, in order to do that, we needed to use 10 times the number of spindles. Again, we're short-stroking the spinning media. Short-stroking means that you are formatting the drive to use only a small portion of the physical capacity, and typically that's going to be the outer tracks within the physical platter, and that means that the disk head is only moving through a much smaller arc, so it's much faster to seek from between pieces of data. So we had 34 devices for the data and 4 separate devices for the log. Same workload, same server, same configuration, same sustained I/O, with 10 times the number of spindles, significantly higher latency. If you look at the first line there, the seconds per read and then seconds per write, they're significantly higher, and the throughput is slightly lower. So although SSD media is significantly more expensive per gigabyte, if you look at what it takes to accomplish an OLTP workload, there are times when it's very economical. And in addition, you may consider that those 10 times the number of spindles, those extra 36 spindles, each require power, they require shelves to house them, they require cooling, heating and cooling, environment, floor space. All of that adds up very quickly to increase the cost. So the economics aren't what it might initially seem like. We talked about looking at checkpoint operations and their impact on throughput. Here's an example of how the size of the write cache on a SAN array impacts the performance of the system as a whole. You see in blue a checkpoint operation. See the big spike of operation, and right after the operation, the red line, which is reads per second, drops way down. Why would a burst of writes cause a subsequent drop in read performance? It's because that burst of write activity filled up the cache on this array, and the array was busy destaging those writes back to disk. It had no room to bring data into the array's cache for future reads, so the future reads were slower. Contrast that with a system, same workload, same server, with a much larger write cache that smooths out that effect significantly. So it doesn't make it go away, but it can help significantly. Switching gears yet again, we're going to talk a bit about I/O do's and don'ts for data warehousing workloads. Unlike OLTP system where you're sizing for I/O per second metric, here you're going to look at aggregate throughput, or megabytes per second. So how fast can you scan all the data in a table? So don't consider only the number of spindles needed for this. You also have to look at the other components in the chain. Controllers, switches, HBAs. As we saw in our example, even the number of cores and processors can be a bottleneck. So you have to look at the entire path end to end and make sure you understand where your bottlenecks are and that there's no bottleneck that is smaller than what you need performance-wise. Know the limits of your path. Consider your aggregate connectivity limits, host, switch, array. Switches have limits. Each connection between a component has a limitation. Arrays have service processors, so they're a special purpose computer. So remember that in our example we had no array controller service processor, and the bottleneck was the processors within the host computer. You can also have bottlenecks within the service processor of the array itself. I've seen that in some examples as well. Range your table scan workload description. It's going to be query plans using range and hash merge, aggregation queries, typical for data warehousing workloads. SQL Server will do Readahead to the extent that we can. We're going to dynamically adjust the size of the I/O based on page continuity. What does that mean? So as long as the pages are in order physically in the database, we're going to read large blocks of data and try and guess which data will be accessed next. To the I/O system, that's going to look like sequential I/O, up to 512K block sizes. There's a SQL Server statistic, DMDB index usage stats will look at some of the statistics for how you're using your indexes, look at user scans. Access methods counters have range scans per second and table scans per second, which will look at how many times you're scanning your sets of data. Readahead pages and the buffer manager counters will tell you how much you're getting from your Readahead within SQL Server, because again, SQL Server has its own buffering to try and keep ahead of that. Quickly, we talked in terms of Readahead and physical fragmentation. So in your B tree, as it's laid out on disk, if the leaf pages aren't in the order of your primary key, you're going to have problems because you've got out-of-order pages. So that breaks the sequence. If you're trying to scan in order, you're going to have to jump around back and forth within the data pages. And that, again, can disturb your ability to read ahead. Once it's in memory, it doesn't matter if it's out of order, but if on disk it does, because you're moving that head back and forth to get to the different pieces of data. And this is an example of extent. So extents are units of allocation within SQL Server. So we'll mix pages from different indexes within an extent. If you have mixed extents like that, then if we're trying to grab a block of pages for index 1 and we come across some pages from index 2, we may grab this whole block still, but those pages aren't going to be used, so it limits the effectiveness of the read-ahead. If there's too many pages of non-useful indexes in between, that means we're going to break it up into multiple IOs, which are also less efficient. So we issue a large number of asynchronous read-ahead requests. So we're going to try and get ahead of where the application is reading pages. We're going to anticipate the need for data, and hopefully the IOs are satisfied by the time we actually get to reading that data. IOs are issued at a rate needed to keep the CPUs busy. We're always aiming to consume all the CPU capacity we possibly can. Size of the IO is going to depend on how contiguous the data is on disk. You can observe the size of the IOs consumed in the read-ahead by looking at some counters, average fragment size exposed by the index physical stats. So looking at a query plan for read-ahead, for an unordered scan, you're going to be looking at pages, allocation map pages to determine the next range of pages. We'll issue one IO for each contiguous range of pages up to 64 pages in a single request. A key order scan is going to be much more efficient because you're looking at a range of pages determined by looking at the B tree for the next range of index scans. Looking at clustered index, first we go through the B trees to find the next range of pages to request based on key order. So if we're looking, the next range is keys A through B. We're going to find the highlighted pages, all part of that request. We're going to arrange them in physical order, grouping contiguous pages, so you'll see the first group of contiguous pages. So we're pulling them in physical order, issue the IO, and your requests are satisfied. A very quick bit about analysis services. It's a completely different storage engine again. IO patterns can be highly random. Block sizes are 32 to 64K. Very wide and shallow IOPS. What does shallow mean? It means that you're not having a queue depth of very deep, which can limit the performance of your IO system. Low latency is very advantageous because you're completely servicing the IO end-to-end, and fragmentation on the disk is often high because you're recreating files very frequently as you rebuild cubes. Analysis services doesn't use the data files to stripe. You can have a striped files, striped storage volumes, but the files themselves don't internally stripe. Looking at analysis services on SSD devices, because of the I/O patterns within analysis services I/O, they see a very significant speed up because of the random nature of their I/O. They benefit from the virtually no seek time within SSDs. So for bank risk analytics, the workload saw a 10x speed up. Sales reporting was a 7x speed up. Some things to consider: increasing your thread pool for the process, partition the cube between NAND and spinning media, in other words, based on your, again, class of data. And that's the presentation that I have for you this morning. I hope you found it useful. And with that, I'll turn it back to Rachel.
Hey, Kevin, we have a couple questions in the box. Do you have time for questions, or do you have somewhere else to be?
I've got a few moments.
Okay. I'll start with someone said early on how auto tiering is done in SQL Server environment.
So auto tiering is done by the array itself. SQL Server doesn't actually have any direct role in that. What it is the SQL Server files are stored on the array, and the array observes how frequently different parts of that data are accessed, and in the background will migrate the data to the different classes of storage based on the array's anticipation of how frequently that data will be accessed in the future based on past access patterns. And again, they do track a history on ranges of data. Different arrays migrate data at different granularities. Some of the early auto-tiering systems were at the LUN or volume level, so move a whole volume. Other arrays are getting into smaller and smaller units.
Okay. How do you calculate speed core?
Speed per core is based on observation. So for a class of processors, we will actually benchmark it. We'll lay out a configuration where we guarantee that the CPU is going to be the bottleneck for I/O. In other words, we'll use enough storage that the storage is never the bottleneck. We may use Fusion I/O style storage, which can deliver just enormous amounts of performance, and find out where the system bottlenecks on the CPU, divide by the number of cores, and set the expectation for that generation of processor.
Okay. And do you recommend solid-state drives for TempDB?
If TempDB in your configuration is a performance bottleneck, that can be a very effective way to increase your performance of the overall system.
And Flora says, should we defragment our physical drives if they are part of a SAN?
Defragmenting the files in the file system can be advantageous. Most SANs are going to be doing write-ahead, so they'll be writing the data not necessarily in physically contiguous order, although they do the aggregation at the array cache level layer, so you don't necessarily see that. It's always best to have as contiguous storage as you possibly can. SQL Server allocates the files once, so we create the big file and then just live within it. We're not constantly creating new files, so unless you're growing files, you're typically not going to see a lot of fragmentation within SQL database files.
And last one, it says, do you recommend SSD or SSAS?
I'm not sure what acronym they're meaning by SSAS. So SSD, solid state device, is definitely useful if you're talking about the class of storage that plugs directly into PCIe buses. Those can be extremely fast. Did you have a response?
Sorry, I may have read that wrong. It says, do you recommend SSD for SSAS?
Yes, I would, because the SSAS workload tends to be more randomized, and that's the I/O pattern that SSDs excel at, because there's no physical head to move back and forth. Seek times are virtually non-existent, so SSDs are very useful.
Okay, and I had a lot of people request if you could make your slide deck available. That's up to you. And if you could just send that to me, and I could pass that along to those that are interested.
Okay, I can do that.
And just as a reminder, everyone, the sessions are recorded, so those will be made available by the end of the week, so you can go back and review. If you go to pragmaticworks.com, go to webinars, and you'll find all of our past webinars in one little section for you. So that should do it for us, and I appreciate you taking the time to present with us today. And we look forward to having you back again.
All right. Thank you.
Okay, thanks. Enjoy your long weekend.
You too.
Thanks. Bye-bye, everyone.